Okay, hi, so thank you all for coming. Today I'm going to be giving a talk about dark energy. So I've called my talk, What on Earth is Dark Energy? I'm going to spoil the question and tell you the end of the talk before I start, which is the answer is I don't know. I will not be answering this question today. If I knew the answer to this, if I knew what dark energy was, I would probably be off writing papers and winning Nobel Prizes rather than talking about it. But at the very least, dark energy is a very, very fascinating subject. And so I want to at least give like an outline of the problem and why we care about it and about where we are in our current state of thinking about dark energy. So I think I always like starting talks with this image just to remind people that, you know, astronomy is an old science. People have been trying to understand the workings of the cosmos by looking at lights in the night sky for pretty much as long as there have been people, right? People have been coming out and looking at vistas like this and trying to understand the workings of the universe. So there are various things you can see in here, of course. You can see our Milky Way galaxy and the stars. I showed this to a group of school children a few months ago, and I asked them, you know, what do you think this is? And they said it was a tree, which, you know, not exactly wrong, but I think I need a new picture maybe. But the thing that's relevant for this talk today, and the thing I want to draw your attention to, is this Milky Way galaxy, right? This kind of strip of light across the sky. And so that's fascinated people, obviously, for thousands and thousands of years. And it was only relatively recently in human history, with the discovery of telescopes and so on, that we began to understand what our galaxy really looks like. So this is what our galaxy looks like from the inside. But if you could kind of fly out of our galaxy and see our galaxy from the outside, it would look more like this, with us being about 2/3 of the way out. So this is what our Milky Way galaxy looks like from the outside. We're a fairly large galaxy, about 100,000 light years across, and containing somewhere between 200 billion and 400 billion stars. And this is really where the curtain comes up on what we call cosmology, like in the efforts to understand the entire universe. This is really the beginning of modern cosmology, which starts about 100 years ago. Because about a century ago, we knew various things, and the two main things that we believed to be true about our universe a century ago were, firstly, that the Milky Way was the only thing in the universe. Right, so we thought a picture like this was pretty much a picture of the entire material universe, and there was nothing really outside. But secondly, and more importantly for this talk today, the other thing that we thought about the universe was that it had been around forever, right? That the universe was infinitely old and specifically unchanging, right? So the universe had been around forever in exactly the same state. Nothing was going on with it, right? It was just unchanging. Both of these things got overturned in very, very quick succession by this guy, Edwin Hubble, one of the most famous astronomers of all time. I imagine most people here would have heard of him. I think he became more famous in the 1980s, 1990s onwards because he had the Hubble Space Telescope named after himself, right? I always figure you're doing pretty well if you get a multi-billion-dollar piece of equipment named after you, right? And so Hubble is justifiably famous. So Hubble's big breakthrough, and that let him overturn these two kind of pillars of our understanding of the universe, was that he found the first evidence for the fact that our universe is expanding, right? So remember I said that was the one of the things that we thought about our universe about a century ago, was that it wasn't changing over time, right? It had been around forever, it would be around forever in the future, just completely unchanging. Hubble was able to show that is actually not true, and that the universe is actually expanding with time, right? The universe is getting bigger and bigger and bigger with time. And this paved the way for all kinds of interesting discoveries, and particularly this paved the way for learning that our universe started with a big bang, right? If your universe is infinitely old and unchanging, then you don't need a beginning. But as soon as you have a universe that's growing and changing over time, as Hubble discovered, there needs to be a beginning point that kicked off the growth. So Hubble's big discovery that the universe was expanding led to us understanding that there was a big bang as well. It was a transformative time in astronomy. This was his famous paper. It has a fairly unassuming title. I don't think you would realise the importance of this paper from reading the title. a relation between distance and radial velocity among extragalactic nebula. So extragalactic nebula being what they previously thought were kind of little whirly clouds within our own galaxy that Hubble was able to show are actually galaxies millions of light years away. So this is a very famous paper. This is the first evidence for an expanding universe. It's one of the most important scientific results of all time. Hubble was very modest, and there's this lovely quote in the paper where he says, "New data are coming in the future, and for this reason it was thought premature to discuss the obvious consequences of the present results." So Hubble knew he had something very, very big, but he was too cautious to, he was too cautious just to kind of go shouting his results from the rooftops, right? So he trusted the reader to understand the enormous implications of what he was saying. The other thing I want to point out as well, really draw your attention to, is the date up here. So it's January in 1929. The reason I'm pointing that out is that I really wanted to sink in, like, how recent that was relatively, right? I mean, this is one of the biggest discoveries of all time, that our universe is not just static and unchanging, but is growing over time. The expanding universe is one of the most important scientific things we've ever discovered. And it's really relatively recently, right? 1929. It's less than 100 years ago. For reference, that's within my grandfather's life, right? It's really not very long ago we had this completely transformative change in how we saw the universe. What I think on this note as well, it's also particularly interesting to remember that 1929 is actually after Einstein was working and after Einstein was coming up with his theories of relativity, which described the universe. So that always amazed me to think, right, that when Einstein was writing down his theories of relativity to explain the universe, he didn't know that he lived in an enormous expanding universe. He thought he lived in a small universe that was unchanging over time. So that'll be of relevance later, so remember that. So like I said, it was a very transformative time for astronomers. You almost feel sorry for astronomers at the time, right? They went from thinking that the universe was very, very small and unchanging to knowing that our Milky Way is just one tiny part of a unimaginably vast cosmos. And not only that, but the universe is getting bigger and bigger and bigger all the time. It was a decade of unbelievable transformation in astronomy. So once we've established that, that's really the beginning point for what I'm talking about today, the expanding universe, right? The discovery that the universe began with the Big Bang, and ever since then has been growing and growing and growing. And so, once we understand the expanding universe, once we're comfortable with this idea, we can ask a very important question, which is, what does our universe look like in the future, right? So this is my timeline of the universe. So if the universe started with a Big Bang, and then sometime later there's us, what happens in the far, far future of the universe? Because if the universe is just growing and growing and growing, is the universe just going to get bigger and bigger and bigger and bigger forever? So that's something that this is something that we want to discover. Because there are different forces at work in the universe, right? And so this is a good way of thinking about the future of the universe. So we know from observations that galaxies are all moving apart, right? This was Hubble's big discovery. It's been confirmed over and over again that galaxies are all moving apart as the universe expands. But we also know that gravity exists, right? Gravity is this universal force that fills the universe. Every piece of matter in the universe attracts every other piece of matter in the universe through the force of gravity. And so, if you think about it, gravity should be kind of acting as a brake, if you like, slowing down the expansion. Because as the universe expands and everything moves away from each other, the force of gravity should be trying to pull everything back together and almost acting as a brake. So, this leads you to what seems like an obvious conclusion, which is that the expansion of the universe is maybe slowing down, right? Because the expansion of the universe after the Big Bang, the universe is getting bigger and bigger and bigger, but gravity is trying to pull everything back together. So maybe the expansion of the universe is actually slowing down. So there's a nice and easy thought experiment we can do at this point, because it can get a bit abstract, thinking about expanding universes and gravitational forces and so on. Luckily, because we evolved on a planet that has gravity, we actually have quite a good intuitive understanding of gravity and its effects. So we can kind of bring this stuff down to earth a little bit and do a bit of a thought experiment. So rather than thinking about expanding universes and so on, I just wanted to think about going out into a park and throwing a ball in the air. So, okay, so let's do that experiment, right? So let's imagine that you're me, for example, and you're going out into a park, and you're going to get a ball, and you're going to throw this ball in the air. And so the question I want to ask is, what happens next? And so the answer really depends on how hard you throw the ball, right? The answer to what happens next depends on how hard you throw the ball. Okay, so with a normal throw, you throw the ball in the air, and the ball is going to go higher and higher and higher, but the whole time, gravity is going to be pulling on it, right? So the ball's going to be getting slower and slower and slower the whole time. And eventually, it will reach some maximum height, and then at which point it will start to descend because gravity will pull the ball down, and eventually it falls right down back to the Earth's surface, right? So that's what happens with a normal throw. If you were to throw the ball a bit harder, right? So say you could throw the ball really, really hard. Like say you're Superman, right? If you're Superman, you could throw the ball hard enough that you throw it into space, right? So if you're Superman, you could throw the ball with sufficient strength that the ball would travel up and up and up and up and up and could escape the Earth's gravity altogether and escape off into space. And so, just to kind of make the analogy clear, right? So what's happening here? The throwing of the ball is like the Big Bang and the universe expanding, right? And the gravity of the Earth trying to pull the ball down is like the gravity of the universe trying to pull everything together. Then these two different stories, so first of all, you throw the ball, gravity pulls it back down, or you throw the ball hard enough and it escapes the Earth's gravity. These are two different possible futures for the universe. So depending on how strong gravity is and how fast the expansion is going, the universe might, expand and expand and expand and then reach a maximum size, then eventually get pulled backwards down to nothing, and the ball falling down to Earth. Or if the expansion is going fast enough or gravity is weak enough, the universe, like Superman throwing the ball into space, might just expand and expand and expand forever. So this is, just to make things a little bit more scientific, this is a kind of a cartoon graph about how that would work. So this is a graph of, on the left here, I've labelled it distance between galaxies. You can also think of it as just the size of the universe, right? And then on the bottom here we've got time going forward with, kind of in the past here and then going forward to the future here. And we know that right now the universe is getting bigger, right? That was Hubble's observation, remember, that the universe is expanding. So we're at some time in the universe here, and right now the universe is expanding and getting bigger. So one possible timeline for the universe is that it does something like this. Right, so the universe starts with a Big Bang, and the universe gets bigger and bigger and bigger and bigger and bigger, and then right now it's expanding, and eventually it hits a maximum size, and then gravity eventually kind of starts to beat the expansion, and then gravity just wins, and the universe collapses down onto itself and ends with something that scientists often call a big crunch, right? So the opposite of a Big Bang, the universe just getting squished down to nothingness. But alternatively, if gravity is a bit weaker, or if the expansion is a bit more energetic, what might happen is that the universe could start with a Big Bang, and then get bigger and bigger and bigger and bigger and bigger, and then eventually, just like Superman throwing the ball into space, it might escape gravity and kind of expand forever. So these are two possible timelines for the future of the universe, right? We might live in a universe that's heading for a big crunch, or we might live in a universe that is heading to an infinite just kind of expanding off forever and beating gravity. And so the real question for scientists is which one of these things is true, right? How do we do an experiment to work out whether we live in a universe that's heading for a big crunch, or whether we live in a universe that's destined to just expand forever? And so you'll notice, right, so this is only a cartoon graph, right? This is my kind of cartoon of what's going on. But you'll notice that if this is us here now, you'll notice that in the past, if we're looking back in time, these two tracks diverge, right? The red universe that's destined to expand forever it looks different to the blue universe that's heading for a big crunch. And so all we need to do is look back in time and measure the size of the universe in the past. And if we do that accurately enough, it should let us know which one of these tracks we're on, right? Whether we're heading for a big crunch or whether we are kind of destined to escape gravity and expand forever. And so, so this is the experiment we did. Right, so this was a big experiment that was done by astronomers in the 1990s. It's called the Supernova Cosmology Legacy Survey. And the job of this thing was to look back in time and measure the size of the universe in the past. Which sounds fairly fantastic until you realise that astronomy has this neat feature, right, where looking far out in space also means you're looking back in time, because light can only travel so fast, right? So when you see things at a distance, you're looking at it in the past. So I'm seeing you guys as you were maybe, a microsecond ago, because the light takes, a microsecond or even a few nanoseconds for you to reach me. But the sun is much further away. The sun is 100 million miles away, more or less, and so the light takes about 8 minutes to reach us. So we're seeing the sun as it was 8 minutes in the past, right? And so we can extend that to really, really, really distant things. And so if we look at a galaxy that's many, many millions or even billions of light years away, we're seeing that galaxy millions or billions of years in the past. So, so the goal for astronomers was just to look at lots of very, very, very distant galaxies and measure the average distance between galaxies in the past to get an idea of the size of the universe in the past. And that would tell us whether we're heading for a big crunch or whether we're heading for whether we live in a universe that is going to escape gravity and expand forever. So the question for astronomers was how to do this, right? Because we need to measure the distances between galaxies, right? When we measure one of these galaxies far, far in the past, these very distant galaxies, we want to measure the distances of these galaxies very accurately. This is actually reasonably, simple. Simple is probably the wrong word, right? This is possible because nature has been very, very kind to astronomers and given us something that we can use as like a natural ruler in space, if you like. And that's something called a type 1a supernova. So some of you might have heard the term supernova before, right? So a supernova is the name we give to a dying star when it explodes. A type 1a supernova is not that, slightly confusingly. It's a very, very special kind of phenomenon, which is caused by a white dwarf exploding, right? So white dwarfs have this very unique property, which is that they have a very strict mass limit. And if white dwarfs get too big, if they take one step over this mass limit, they explode. So what can happen? You can often have a white dwarf orbiting a normal star, and then the white dwarf will steal kind of stellar material from the atmosphere of this star. And then the white dwarf, kind of gobbling up all this material, can get more and more and more massive, as it is called accreting mass. And then it can get more and more and more massive, and then eventually it trips this mass limit and explodes. And this is our type 1a supernova. And these are great for lots of reasons, right? They're great firstly because they are very, very bright. So when one of these goes off, even at very, very massive distances, we can see it really, really clearly. The other reason, and the main reason these are really useful, is because astronomers can use them as what we call standard candles, right? And so that's because whenever one of these white dwarfs explodes, like this, the mass at which white dwarfs explode, right, this mass limit which causes them to blow up, is set by very fundamental physics. And so every single white dwarf that explodes like this anywhere in the universe will be exploding with exactly the same mass limit, which means that every one of these explosions we can see in the universe will have the same amount of energy in it, which is really, really useful. Because that means if we compare how bright it looks, like in our telescopes, and we know how much energy is in that explosion, the only thing we have to work out then is how far it is away. And that's very, very easy to do. And so that's it. That's why we call them standard candles. They're really, really useful. So if this is me sitting in this galaxy over here, this picture is not to scale, right? So if this is me sitting in the galaxy over here, and we see a type 1a supernova going off in one of these galaxies, we know how bright it looks, we know how bright it really is kind of underneath, And that immediately lets us work out the distance and lets us use it like a kind of cosmic ruler. It's super useful. So I'll show you the data as it came in, right? So from this famous cosmology survey. So the data from these white dwarf explosions look like this. Which was very surprising, right? No one expected the data to look like this. We thought we were going to be on the red track or the blue track, and when you fit a line to the data, it looks like we're on this completely surprising and unexpected track that's doing something like this. So the answer to this was none of the above, right? Scientists were expecting either to be in a big crunch universe or to be in a universe that kind of just escapes gravity, like Superman throwing a ball into space. And it turned out to be neither of these. In fact, it turns out that we are living in a universe that looks like it's accelerating. And so by accelerating, I mean the speed of the universe's expansion is actually getting faster and faster and faster. And that's not what we expected, right? We expected that gravity would be kind of pulling on the universe and pulling on the constituents of the universe and would be slowing down the expansion. And the question was, would it slow it down enough to win and crush the universe back to nothing? But it turns out the opposite is true. The expansion, rather than slowing down, is actually speeding up. Right? The universe is getting faster and faster and faster. So to take it back to Earth and take it back to our throwing a ball in a park analogy, it's kind of like you going out to a park and throwing a ball in the air, and the ball doing something like this. Right? You kind of toss a ball gently in the air, and then it gets whisked up in the sky faster and faster and faster, and then zooms out of sight. I mean, if I saw that, I would think that was the most bonkers thing I ever saw, right? That would be completely mind-blowing. But that is what's happening to our universe. And so, if you imagine this happening to you, right? If you imagine throwing a ball up in the air and, and then seeing it get whisked out up into the clouds, you would have to think there was some kind of force or something. There'd have to be something doing it, right? There'd be some kind of force carrying that ball off into the sky. And that's kind of the problem that we have in the universe, right? So we see the universe being pushed apart faster and faster and faster, and so it looks like there's some kind of force in the universe pushing it apart faster and faster and faster. And so the question now is to understand what this mysterious force is, right? What is this thing which pushes it apart faster and faster and faster? So the kind of the placeholder name we give for this is dark energy, right? So dark energy is this, it's what we call this mysterious, invisible force that seems to be pushing the universe apart faster and faster and faster. Don't let the fact that we've given it a name lull you into thinking we understand it. Astronomers often put the word dark in front of things to mean we don't understand, right? So dark matter is some kind of mysterious, invisible matter we don't understand. Dark energy is a mysterious, invisible energy that we don't understand. But even though we don't understand it, it's incredibly important. It seems to be, a massive part of what is driving the behaviour of the whole universe. I really think the discovery of dark energy is one of the most important discoveries of all time. Most science journals and science magazines have called it the breakthrough of the year. When it was discovered, it led to Nobel Prizes for the team leading the efforts, even though they don't yet understand what it is, right? The mere fact that they discovered this effect was Nobel Prize worthy. So this is very, very important step that we need to understand. So the question, of course, is what's going on, right? So normally when you have observations of a strange phenomena that you don't understand, and they don't agree with what you expect, there are two different ways you can resolve this problem, right? So either you need to predict some kind of new thing, like causing the weirdness, or you kind of have to go back to the drawing board and admit that your theory was wrong, right? And so in terms of dark energy, what these two things are, so a new kind of thing would be like some energy or something filling the universe, right? So just like you would expect there to be some energy or some force that kind of whisk your ball off into the sky. Maybe dark energy is some kind of mysterious energy that fills the universe that's pushing it apart faster and faster and faster. Or alternatively, maybe we have to go back to the drawing board and admit that we don't quite understand how gravity works, right? Maybe that on very, very, very long scales, the size of an entire universe, gravity kind of repels a little bit. We don't totally know which one of these things it is. I think the answer is almost certainly option one. Many people have tried to do the equations of gravity to work out how it might cause this dark energy effect. No one's ever been able to make it work. And so we are reasonably confident that what dark energy will turn out to be is some kind of mysterious energy or thing that fills the universe. But the quest now is to understand what that is, right? What exactly is this energy that seems to be pushing the universe apart faster and faster? There's a really nice historical story at this point, because this idea that there might be some energy filling the universe and kind of pushing the universe out actually has a really interesting historical origin. So the idea was first floated by Einstein, amazingly, but in something that he ironically called the greatest mistake in his life, right? So he came up with this idea originally, but then he completely went back on it and said it was the biggest mistake he ever made. So if you remember back to the start of the talk when I was talking about Hubble's discovery of the expanding universe, remember I said that Einstein was coming up with his theories of relativity before the discovery of the Big Bang and the expanding universe. So when Einstein was writing down his equations that describe the universe he was trying to describe originally was static, right? It wasn't growing, it wasn't shrinking, it just stayed the same forever. So Einstein, if you imagine a static universe, this is the universe obviously. So if you imagine just plonking a static universe down there, Einstein knew very well that gravity exists, as we said before. Gravity is going to try and squeeze your universe together, right? So if you just put down a static universe, gravity would eventually squash it down together, right? Gravity will act to compress your universe. But he didn't want that, right? He wanted a universe that just stayed the same the whole time. And so he invented this force that could hold up the universe against gravity. So he called it the cosmological constant, right? And so it was this force that he kind of theorized that would act against gravity, that would act and push back against gravity and hold the universe up and stop it from collapsing. So it kind of acts like a skeleton or like scaffolding for the universe, right? Resisting the gravitational collapse. And yes, and like I said, he called this the cosmological constant. The problem, of course, for Einstein is that Hubble came along with his discovery that we spoke about before and said that the universe is not actually just static and unchanging, the universe is expanding. And so as soon as you know that the universe is expanding, that means you don't need a cosmological constant to hold it rigid, right? If the universe is expanding, you can get rid of your cosmological constant and the universe can just happily get bigger and bigger and bigger forever. But now, so this was coming up to 100 years ago, right? But now, in a kind of an amazing twist of history, we have now discovered this effect which we call dark energy. And it does seem to be that there is some force in the universe kind of pushing back against gravity and making the universe go faster and faster and faster. So it could well be that the thing that Einstein kind of theorized, even though he theorized it for the wrong reasons, he might have actually turned out to be right all along, right? That there's this mysterious force in the universe. And so the question is, for theorists now, is how do we make this work theoretically? Where does this come from, right? Because if there's this energy or force in the universe that's kind of pushing it apart faster and faster, we have to kind of understand from a theory point of view where it comes from. And luckily, if you open your physics textbooks, there is actually a way in a branch of physics that predicts that there will be something that looks like Einstein's cosmological constant. So it's a branch of physics called quantum field theory, which you don't have to worry about what that means. It's just a type of theoretical physics. But if you open your textbook, this branch of physics does make a prediction that empty space will have some amount of energy in it, which will actually kind of push outwards, right? So this branch of theoretical physics, quantum field theory, does predict that empty space kind of will push back a bit. And so, at this point, you might say, kind of fantastic, job done, right? I mean, we have an observational fact that the universe seems to be accelerating and it kind of looks like the universe is full of some energy pushing it apart. And then when you open your physics textbook, we see that there are physics theories that predict that there will be some energy in space that will act like a cosmological constant and push the universe apart. But there's a small problem with this. Before we kind of say job done and go home, there's a problem with this, which is that your physics textbook kind of predicts how strong this effect should be, and it gets the answer wrong, right? So theoretical predictions disagree with what we actually see in the universe for how strong this effect should be. So like I said, so theoretical predictions get the answer wrong, but by wrong I do mean very, very wrong. And by very, very wrong, I mean pretty much the wrongest a theoretical prediction has ever been. Right? It's been called the biggest difference between like textbook prediction and what we actually see in the world in the entire history of science. So in fact, theory predicts a dark energy that is larger than we actually observe, right? So your textbook tells you it should be stronger than what we see in the universe. And theory predicts it should be stronger by a factor of this number. So that's 1 with 120 zeros after it. It's a number so big it doesn't even have a name, I don't think. So this is the reason that people say it's the biggest, one of the biggest mistakes, biggest problems in the history of science, right? The difference between the theory and observation is 1 with 120 zeros after it. So there's a very big mistake somewhere that we have to solve. And this is kind of where we're up to, right? So this is the end of the talk, almost because it has to be, right? So we have this fantastic observation that the universe seems like it's full of some mysterious energy that's pushing it apart faster and faster and faster. We don't really understand it yet. And one thing I just want to end with a point that even though we don't understand this stuff, I think for a scientist that's actually kind of exciting. Right, so people use iceberg analogies quite a lot for saying about stuff that we see and stuff that we don't see. In the case of like our understanding of the universe, an iceberg analogy is actually quite apt, because something like 5% of the universe is stuff that we understand, right? Like me and you and the planets and the stars and all the stuff that we understand well is only about 5% of the universe. 95% of the universe, and most of that is this dark energy that we don't understand, is unknown. All right, so we really are in a situation where we only understand the tip of the iceberg of the universe, and the majority of all the stuff in the universe, most of which is this mysterious dark energy, we have very little idea. We have very little idea about what it is. So while it might seem daunting to not understand what most of the universe is made of, I think scientifically it's actually really, really exciting, right? It's like being right on the verge of a kind of big unexplored vista, right? So I think it's almost certain that the coming decades in cosmology and our understanding of the universe are set to be really, really exciting.